From the powders that we use to produce pharmaceuticals to the solid rocket propellants used to launch humanity into space, granular materials are present in almost every facet of our world. A granular solid is defined as a collective system of discrete, solid, macroscopic particles. While most materials can be classified as solids, liquids, or gases, granular materials have unique multi-phase characteristics that give them the ability to behave as all three. In fact, their complex behavior has led many to characterize granular materials as a new form of matter entirely. Discoveries in the field of granular solids are critical to creating efficient systems in areas such as agriculture, manufacturing, and medicine. Due to their wide-ranging applications, granular solids constitute trillions of dollars of the global economy and are the second most handled material in the world after water. At the NJIT Granular Sciences Laboratory, our goal is to further groundwork in the behavior of granular solids. Our research aims to develop dynamical systems that accurately model and predict the behavior of granular media under a wide variety of flow regimes. In particular, we investigate the density relaxation process in bulk solids. That is, the changes in the bulk density of a granular system as it undergoes a series of discrete percussions. Our model uses idealized particle assemblies, consisting of monodisperse, frictional, dissipative spheres based on the soft sphere models of Walton and Braun. The spheres were intentionally chosen to be monodisperse in order to eliminate the effects of varied particle geometry and to isolate the parameters that affect microstructure evolution. The computational geometry of the system consists of a laterally periodic rectangular container with a solid floor and an open top. The particle assemblies are subject to a series of perturbations or taps of amplitude A and frequency omega. Each tap is characterized by the non-dimensional acceleration, defined as gamma equals A omega squared over g. For each tap, the program outputs positional data that is used to calculate the ratio of the volume of solids to the volume occupied, known as the solids fraction. The particle dynamics are governed by the soft sphere approximations of Walton and Braun, where the normal force model admits a constant coefficient of restitution given by square root of K1 over K2, where K1 is the loading stiffness and K2 is the unloading stiffness as shown in the graph. The tangential force model is based on the theoretical findings of R. D. Minlin and H. Derezowicz. It uses tangential stiffness, K sub t, which decreases to zero with increasing tangential displacement, at which time the contact slides at the friction limit mu. The simulation begins by generating 3,600 randomly positioned idealized particles within the envelope of the container. Next, we generate a randomly ordered loose assembly by turning on gravity and allowing the particles to settle in the container until the kinetic energy effectively reaches zero. Once the assembly is fully equilibrated, it is tapped by applying a half-sine velocity to the rigid floor of the container. Energy from the moving floor is transmitted to the assembly, which causes it to expand, rearrange, and contract until it equilibrates. Once the particles have settled to a stable state, the particle positions are recorded, from which the solids fraction at that tap is computed. This tap settling sequence is repeated multiple times. In all, the simulation is performed for 25 initial configurations, i.e. realizations, with equivalent statistical distributions, each undergoing 15,000 taps. The simulation is repeated for 2 values of gamma, aggregating a total of 750,000 data points. These values are subsequently plotted to analyze the density evolution of the system. Early studies of closed sphere packing found that randomly packed spheres of similar size can achieve a solids fraction of 0.64, known as the Bernal limit. Multiple studies on granular dense packing conducted since then have found that randomly closed packed spherical assemblies can achieve solids fractions ranging from 0.56 to 0.641. Highly ordered geometric configurations of monosphere assemblies were found to attain a packing density of 0.74, defined mathematically by pi over 3 root 2. For our analysis, we plotted the solids fraction as a function of tap number in order to analyze the density evolution process for each of the 25 realizations, shown in different colors. The first plot shows the density evolution process for gamma equals 2.75. While most realizations reveal minimal evolution from their initial solids fractions, others display substantial leaps in solids fraction values as the tap number increases. We can identify two clusters of solids fractions. The first occurs at around 100 taps, with an average solids fraction of about 0.641. The second occurs at about 2,700 taps, with a solids fraction of about 0.7. The maximum solids fraction for this value of gamma is 0.72 and occurs at around 12,000 taps. When gamma is increased to 3.25, we notice a substantially larger number of leaps in solids fraction. Again, two clusters can be identified. The first cluster occurs at around 300 taps, with an average solids fraction of about 0.645. The second, more populated cluster occurs at around 2,000 taps, with an average solids fraction value of 0.7. The maximum solids fraction for gamma equals 3.25 is 0.713 and occurs at around 1,800 taps. For comparative analysis, we plot the average solids fraction per tap across 25 realizations for each value of gamma. On the whole, the average solids fraction values are higher for gamma equals 3.25 than for gamma equals 2.75. We observe that the average bulk density for both values of gamma begin to diverge at around 45 taps. The disparity between the two plots grows rapidly until it reaches a maximum at around 2,000 taps, after which the plots begin to steadily reconverge. We can also note that the transitions in solids fractions for gamma equals 2.75 are noticeably less steady than for gamma equals 3.25, with abrupt leaps in average solids fraction values at various tap quantities. In order to further analyze the solids fraction trends, we apply dimensionality reduction using principal component analysis. PCA consists of mapping a high-dimensional dataset onto a low-dimensional manifold. In this experiment, for each tap, the three-dimensional positional coordinates for each of the 3,600 particles, along with the associated solids fraction, is mapped to a singular point on a two-dimensional manifold, denoted by psi1 and psi2. The solids fraction is indicated by a color spectrum, which varies from dark to light for increasing values of bulk density. PCA, followed by a k-means clustering process, is applied to the particle position data for a single realization at gamma equals 2.75. We observe that the data aggregates into two linear clusters. We can see that the solids fraction variation patterns are still retained even in a low-dimensional space. This PCA process is repeated for multiple realizations. Further analysis needs to be done on the entire dataset that includes all realizations to gather a more comprehensive understanding of the relevant features and data trends. Moreover, while we apply a linear dimensionality analysis, nonlinear dimensionality reduction may give rise to better manifolds that honor the nonlinear nature of the density relaxation process. In summary, our research aimed to analyze microstructure evolution of granular assemblies subject to a series of taps using a DEM simulation. We find that when subject to extensive tapping, the maximum solids fraction for an assembly of monodisperse, idealized spherical particles attains values of 0.71 to 0.72. Our experiment was conducted for 15,000 tap cycles. However, these findings suggest that with further tapping, we may continue to observe leaps in solids fractions. By applying PCA on the positional data, we were able to analyze the bulk state from a pure data perspective. Graphs of the PCA data showed a stratification of the solids fraction associated with the system evolution from random to crystal-like microstructure. Our findings thus far suggest that from a purely data perspective, it is possible to analyze the evolution of granular microstructure by applying methods of deep learning. Our research team is currently trying to develop a machine learning surrogate that will be able to forecast the average solids fraction evolution beyond the training set used to create the model. From the research team at the Granular Sciences Lab at NJIT, thank you for watching our presentation.